Hello everyone, welcome you all to the lecture series about the control system subject. In the previous videos, we have discussed what is the system, that is, what are all the elements present in the system. And the next class, we have discussed about the types of the system. Now we are going to see about the mathematical modeling of mechanical system. So let me explain it in the upcoming slides. What is this mathematical model means? Why we are going for mathematical models of mechanical and electrical system? Because it is useful for analyze and design our system. So we are using the analysis part by means of models. Here we are representing those mathematical models as differential equations. So differential equations, which is a time domain mathematical model of control system. And we have a transfer function model here, which is the S domain mathematical models of control system. Let me explain what is this transfer function. Transfer function, which is defined as the ratio of Laplace transform of output and the Laplace transform of input by assuming all the initial conditions are zero. By this definition, we can able to derive that formula as transfer function which is equal to y of s by x of s. You can see this by in the block diagram. The block diagram that has the control system which has the input of x of s and that produces the output of y of s. In between, we have the transfer function and we are representing the transfer function as y of s by x of s. First thing, we are going to see about the mathematical modeling of translational mechanical system. So, translational mechanical system, which moves along a straight line. So, which has some basic elements, that is mass, spring, dashpot, or the damper. Here, if a force is applied to the translational mechanical system, then it is opposed by an opposing force due to the Newton's law, and those opposing force will be created because of any one of these three elements, and the applied force and the opposing forces are in opposite direction. So the algebraic sum of these forces acting on a system is zero. First, we are explaining the mathematical modeling of translational mechanical system as the basic element of mass. Mass, which is the property of a body which stores kinetic energy. And if you are applying a force which has the system which on a body which has a mass element, and then it is opposed by an opposing force due to that mass. This opposing force is proportional to the acceleration of the system. So we can see Fm, which is proportional to A, that is the acceleration, that produces m into A, which is the mass into acceleration. Here, finally, we can write the F as m into d square x divided by dt square. And this picture will represent how the elements are present. The system, that is the body, which has mass alone, and we are applying the force, which has the displacement of x. So from the equation, F equal to m into d square x divided by dt square, let me explain. F is the applied force, Fm is the opposing force due to the mass, and m is the mass which has the acceleration of a, x is the displacement. And the next element is the spring, which has the capacity of storing potential energies. And here also, we are applying a force on a body, the body which has a spring alone, and that will produces an opposing force due to this elasticity of the spring. Now, this opposing force is proportional to the displacement of the string. And we are assuming that mass and frictions are negligible. Here, F is proportional to x. By removing the proportionality constant, we are introducing a constant called K, which is a spring constant. So finally, our applied force F, which is equal to the opposing force Fk, which is equal to K into X. The K is the spring constant and X is the displacement. And the final translational element is the dashpot. Here also the system which has the dashpot component alone, so that if we are applying a force, it will produce an opposing force which is due to friction of the dashpot. So this opposing force is proportional to the velocity of the body. So assume the mass and the elasticity are negligible here. So Fv, we can proportional to the v, that is the velocity of the body. By removing that proportionality, we are introducing a constant again here, that is B, which is a frictional coefficient. This picture, which explains the system which has a dashpot, and we are applying that force which has X as the displacement. So finally, we are getting the equation as F equal to FB, which is equal to B into dx divided by dt, where F is the applied force, FB is the opposing force due to the friction of the dashpot, and B is the frictional coefficient, V is the velocity here, which has the displacement of X. So I hope you have understand the representation of these three elements. Finally, the mass F we are representing as m into d square x divided by dt square. Spring, we have the force as k into x. Dashpot, we are representing the F, which is equal to B into dx by dt. So let me continue this translational mechanical system in the next video. I hope you have understand the translational mechanical system in this videos. So the mechanical rotational system, which has three basic components, which we will discuss in the next class. Thank you.